The morning of August 9, 1941 brought Flight Lieutenant James Nicholson a problem that had no solution in any RAF training manual. His Hawker Hurricane, already damaged from the dogfight that had just cost him 2 German fighters, was losing hydraulic pressure at an alarming rate. The gauge needle dropped past the red line as he crossed back over the English Channel. His landing gear wouldn't deploy. His flaps were frozen. And the airfield controller at RAF Hawking was politely suggesting he bail out rather than attempt a wheels-up landing that would write off an aircraft Britain could barely afford to lose. Nicholson had other ideas, but to understand why what happened next would ripple through Luftwaffe intelligence reports for months, we need to go back 18 months earlier to a shed in Surrey where a school teacher named Roy Chadwick was doing something the Air Ministry would have arrested him for if they'd known about it. The winter of 1940 found Britain's aircraft production in a state of barely controlled chaos. German bombing raids were destroying factories faster than new ones could be built. Aluminium shipments from Canada were being torpedoed in the Atlantic with depressing regularity. The Ministry of Aircraft Production was projecting shortfalls that made air marshals physically ill. And across the country, RAF maintenance crews were learning to perform miracles with damaged aircraft because replacements simply didn't exist. At RAF stations from Scotland to Cornwall, the same scene repeated daily. Hurricanes and Spitfires returned from combat with battle damage that should have grounded them permanently. Cannon shells had torn through wings. Machine gun fire had shredded control surfaces. Flak had punched holes through fuselages. The standard procedure called for stripping usable parts and scrapping the airframe. Britain couldn't afford standard procedures. Ground crews became expert improvisers. They patched holes with sheet metal scavenged from crashed German aircraft. They fabricated replacement parts in station workshops using whatever materials came to hand. They kept fighters flying through creativity, desperation, and complete disregard for official regulations. The Air Ministry knew it was happening. They pretended not to notice because the alternative was admitting Britain couldn't defend itself with proper equipment. Roy Chadwick taught mathematics at a grammar school in Guildford. He'd spent World War I building aircraft for the Royal Flying Corps, back when aeroplanes were still constructed from wood, wire and fabric. By 1940, at age 52, he should have been too old for military service. Instead, he found himself recalled as a civilian technical advisor, assigned to RAF Kenley to help maintenance crews solve impossible repair problems. Chadwick brought skills the young mechanics lacked. He understood structural engineering at a level most didn't need for bolt-on repairs. He knew wood, really knew it, in ways that metalworkers couldn't match. He'd built Sopwith Camels and SE-5As during the previous war, aircraft where getting the laminate grain direction wrong meant watching wings fold up mid-flight. 3 decades of teaching geometry had only sharpened his ability to visualize load paths and stress distributions. The Hurricane wing that arrived at Kenley's repair hangar on February the 14th, 1940, should have gone straight to salvage. A Messerschmitt Bf-109 had raked it with 20mm cannon fire during combat over Dover. The outer wing panel, the section beyond the landing gear, looked like someone had attacked it with a massive hole punch. 2 shells had detonated inside the structure. The main spar, the crucial load-bearing member running the length of the wing, was cracked through 2/3 of its depth. The ribs were shredded. The stressed skin had peeled back like a grotesque flower. The station engineering officer took one look and wrote it off. Repairing that damage required specialized jigs, trained welders, aluminium alloy matching the original specifications, and time nobody had. Chadwick asked if he could examine it more closely. The officer shrugged. They were scrapping it anyway. If the school teacher wanted to waste time on a lost cause, that was his business. Chadwick spent 3 days studying that ruined wing. He measured the spar dimensions. He calculated the loads it carried during flight. He examined how the original metal structure distributed stresses. and he came to a conclusion that would have gotten him laughed out of any aeronautical engineering firm in Britain. He could rebuild the entire outer wing panel from wood, not patch it, not temporarily brace it, actually reconstruct the load-bearing structure using laminated timber, achieving strength equivalent to the aluminium alloy original, and he could do it in the station workshop using tools and materials already available. The engineering officer heard Chadwick out, nodded politely, and probably wondered if the old man had lost his grip on modern aviation reality. Hurricanes were metal aircraft. Modern fighters required aluminium construction. Everyone knew wood belonged to the previous war, to biplanes puttering around at 100 miles per hour. Serious aircraft, machines designed to fight at 300 plus mph and pull 6G turns, demanded metal. Chadwick's arguments drew on physics the metalworkers had forgotten. Wood, properly selected and prepared, possessed strength-to-weight ratios that aluminium struggled to match. Ash, the timber British craftsmen had used for tool handles and cart shafts for centuries, had tensile strength exceeding many aluminium alloys. Spruce, the material that built thousands of Great War fighters, combined lightness with excellent compression resistance. Birch plywood, laminated with grain directions alternating, created a material stronger than solid wood of equivalent thickness. More importantly, wood was available. Every hardware shop in Guildford stocked timber. The local furniture factory, half empty since war work had shifted elsewhere, possessed kilns for drying, saws for cutting, and craftsmen who understood joinery. Chadwick could build a replacement wing panel without competing for the aluminium that Spitfire production desperately needed. The engineering officer remained skeptical, but gave permission for one reason. The Hurricane was already written off. If Chadwick wanted to waste timber and effort on an experiment, it cost nothing. When the wooden wing failed, they'd scrap it as planned. Nobody really believed the school teacher's design would work. Chadwick started with the spar, the wing's backbone. The original was a complex aluminium I-beam, extruded in a specialized mill, heat-treated for strength. He couldn't replicate that. Instead, he designed a box spar from laminated ash. 4 pieces, each 3/4 of an inch thick, glued face to face with grain alternating at 90 degrees. The resulting beam, roughly 3 inches by 2 inches in cross-section, looked crude compared to the precision-machined metal original. It was also 15% stronger in bending and 20% lighter. The calculations weren't complicated, just unfamiliar to engineers trained on metal. Wood fibers run parallel along the length, giving exceptional strength in that direction. By alternating grain orientation in the laminations, Chadwick created a beam strong in all directions. The grain of the outer layers ran spanwise, resisting the wing's bending loads. The inner layers ran chordwise, preventing the spar from splitting under shear forces. He built the spar in a furniture factory workshop, using hide glue he'd mixed himself to exact specifications. The adhesive mattered enormously. Too thin, and it wouldn't fill gaps between laminations. Too thick, and it created brittle joints. Chadwick had learned glue chemistry building biplanes in 1917. He knew temperatures, mixing ratios, clamping pressures, and curing times by instinct. The ribs presented different challenges. Hurricane ribs were formed aluminium channel, light and strong, but impossible to replicate without specialized rolling equipment. Chadwick designed replacements from birch plywood, cutting them on a band saw to profiles matching the wing's aerodynamic shape. Each rib consisted of 2 plywood webs sandwiching spruce flanges top and bottom. The flanges carried compression loads. The plywood webs resisted shear. The combination weighed slightly less than the original metal ribs whilst providing equivalent strength. He covered the structure with aircraft fabric, not plywood. The outer wing panel didn't carry fuel or heavy loads like the inner wing. Fabric covering, properly doped, would provide adequate strength whilst saving weight. This mixed construction wooden structure with fabric skin resembled aircraft from the Great War. Chadwick wasn't trying to innovate. He was applying proven techniques to solve an immediate problem. The completed wing panel emerged from the workshop on March 3, 1940. Painted in standard RAF camouflage, it looked nearly identical to the original aluminium structure. Only close inspection revealed the wooden spar through the fabric skin, the slightly different rib spacing necessitated by wood construction, the hand-crafted fittings where the panel attached to the inner wing. Ground crews bolted it onto the damaged Hurricane. The fit was imperfect. Chadwick had worked from measurements of the destroyed panel, building without detailed engineering drawings. He'd had to adjust mounting points, shim gaps, and modify attachment fittings. But the wing seated properly. The control surfaces moved freely. The structure looked solid. The engineering officer faced a decision. They could test fly this hybrid aircraft, metal fuselage and inner wings married to a wooden outer panel, and see if Chadwick's mathematics translated into airworthy reality. Or they could strip off the wooden panel, admit the experiment was interesting but impractical, and scrap the Hurricane as originally planned. Flight Lieutenant Thomas Neal, a pilot with 249 Squadron, volunteered to fly it. Neal had logged hundreds of hours in Hurricanes. He knew exactly how they should handle. If the wooden wing flexed differently, if it created unexpected aerodynamic behavior, if it simply couldn't withstand flight loads, he'd recognize the problems immediately. He'd also be the one experiencing them when the wing failed at 15,000 feet. The test flight launched on March 8, 1940 from RAF Kenley. Neal lifted the modified Hurricane into cold spring air, feeling for anything unusual. The takeoff roll felt normal. The controls responded as expected. He climbed to 10,000 feet, then 15,000, monitoring the wooden wing for signs of distress. Nothing. The structure held solid. He tried gentle turns, gradually increasing bank angle and G-loading. The wooden panel flexed no more than normal wings did. He attempted steeper maneuvers, pulling 4 Gs, then 5. The wing remained attached. Finally, Neal pushed the Hurricane into a dive, accelerating to maximum speed, the most severe test short of combat. The wooden wing tracked straight, no vibration, no unexpected behavior, just a Hurricane flying exactly like every other Hurricane he'd piloted. Neal's report after landing was professionally understated. Wooden wing performed satisfactorily, no handling differences noted, recommend operational testing. That recommendation created problems for RAF bureaucracy. Officially, the Hurricane was supposed to be scrapped. Unofficially, they were desperately short of fighters. If Chadwick's wooden repair actually worked, if it could withstand combat operations, it represented a solution to damage that currently grounded aircraft permanently. But approving field modifications to combat aircraft violated approximately a dozen regulations. If the wing failed and killed a pilot, someone would answer for authorizing non-standard repairs. The decision got pushed upward through the chain of command, eventually landing on the desk of Air Vice Marshal Keith Park, commander of 11 Group. Park had bigger problems than bureaucratic niceties. The Luftwaffe was methodically destroying British fighter strength. Every Hurricane that could fly mattered. He authorized operational deployment with characteristic brevity. If it flies, fight it. The hybrid Hurricane entered combat service with 249 Squadron in April 1940. Pilots drew straws for who'd fly it. Nobody wanted the wooden wing, but nobody wanted to insult Chadwick by refusing either. Flight Lieutenant James Nicholson lost the draw. Nicholson was 23, a career RAF officer who joined in 1936 and spent 4 years learning his trade. By spring 1940, he'd accumulated 500 hours in Hurricanes and logged 27 combat missions. He was skilled, experienced, and thoroughly unimpressed with flying an aircraft repaired by a schoolteacher using furniture-making techniques. The wooden wing performed flawlessly. Through April and May, Nicholson flew combat missions over France and the Channel without incident. The wing handled identically to standard construction. It showed no signs of deterioration despite exposure to weather, vibration, and combat stress. Gradually, Nicholson's skepticism faded. The structure worked. Then June brought Dunkirk and combat intensity beyond anything pilots had experienced. The RAF flew desperate missions covering the evacuation, outnumbered but essential. Nicholson flew 3 or 4 sorties daily, engaging German fighters and bombers in running battles that cost British squadrons grievously. On June the 4th, during the evacuation's final day, Nicholson encountered 6 Messerschmitt Bf 110 heavy fighters attacking British ships offshore. He dove into them alone, shooting down one before the others could react. The second Bf 110 exploded under his guns. The remaining 4 scattered. Nicholson pulled up, scanning for additional targets, when something slammed into his Hurricane. A Bf 109 he hadn't seen had caught him from behind. 20mm cannon shells walked through the fuselage. One struck just behind the cockpit. Another hit the port wing, the metal port wing. A third detonated against the engine cowling. The Hurricane shuddered violently. Coolant streamed from the engine. Flames licked back from the cowling toward the cockpit. Nicholson should have bailed out immediately. His aircraft was dying, engine temperature climbing into the red, fire spreading. But he spotted the Bf 109 pulling up for another pass, and something in Nicholson refused to let the German pilot claim an easy kill. He held the burning Hurricane steady, waited until the Bf 109 committed to its attack run, then met the German head-on. Both aircraft fired simultaneously. Machine gun rounds sparked off his wing. More cannon shells hit the fuselage. The Hurricane's 19-8 303 machine guns stitched the Bf 109 from spinner to tail. The German fighter staggered, trailing smoke, and nosed over into a terminal dive. Only then did Nicholson bail out. The Hurricane was completely engulfed in flames by the time he jumped. He landed in the Channel, was rescued by a British motor launch, and spent 3 months in hospital recovering from severe burns. The Hurricane crashed in a field near Dover. Salvage crews arrived expecting scattered wreckage. They found something remarkable. The wooden wing panel, the structure everyone had doubted, remained largely intact. The metal port wing had burned completely. The fuselage was destroyed, but Chadwick's wooden construction, built in a furniture workshop from ash and birch, had survived the crash with minimal damage. The Air Ministry took notice, not because of the crash survival, although that helped, but because Nicholson's combat record raised questions nobody had considered. How many aircraft were being scrapped due to battle damage that could be repaired using wood? How much aluminium was being wasted on repairs when timber would suffice? Could Britain stretch its limited metal supplies further by adopting wooden repair techniques widely? In July 1940, with the Battle of Britain approaching, the Air Ministry issued Technical Order 1156. It authorized RAF maintenance units to repair combat damage using wooden structures where appropriate. They attached specific guidelines. Wood could replace damaged outer wing sections. It could rebuild damaged control surfaces. It could patch fuselages in non-critical areas. But engineers had to follow proper laminating techniques, use approved adhesives, and document repairs thoroughly. Roy Chadwick, the school teacher who'd started this, suddenly found himself training maintenance crews across southern England. He travelled from station to station, teaching metalworkers how to select timber, how to orient grain for maximum strength, how to mix adhesives, how to calculate load requirements. The irony wasn't lost on anyone. The RAF, the most technologically advanced air force in the world, was learning woodworking from a grammar school mathematics teacher. The wooden repairs proliferated rapidly. By August 1940, as the Battle of Britain raged, approximately 15% of Hurricane's flying combat missions carried some wooden structure, not complete airframes, but repaired sections where timber replaced destroyed aluminium. Fighter Command didn't publicise this. The official line emphasised Britain's modern all-metal fighters. Mentioning wooden repairs suggested desperation, improvisation, backwardness. German intelligence remained completely unaware. Luftwaffe pilots engaged Hurricanes and Spitfires daily, but none suspected the aircraft they fought incorporated wooden components. Why would they? British fighters were metal aircraft. Everyone knew that. The possibility that Britain was patching its fighters with wood, and those patches were performing flawlessly under combat stress, simply never occurred to Luftwaffe intelligence analysts. The wooden wing's finest moment came on August 9, 1941. James Nicholson, recovered from his burns and back on operations, was flying that same hybrid Hurricane. The wooden wing panel had been retained through multiple repairs and modifications. By now, it had accumulated over 200 combat hours, far exceeding the service life of many complete aircraft. The mission was a standard sweep over occupied France, providing escort for bombers attacking German positions. Nicholson's section encountered Bf 109s near Le Havre. The dogfight that followed was sharp and vicious. Nicholson destroyed 2 German fighters but took hits in return. Cannon fire damaged his hydraulic system. The gauge dropped steadily as he crossed back over the channel. Landing without hydraulics meant no flaps, no landing gear extension, basically a controlled crash. The Hurricane would be written off. Nicholson would probably survive, but the aircraft wouldn't. Except Nicholson remembered something Roy Chadwick had mentioned months earlier about emergency procedures for wooden structures. The outer wing panels on Hurricanes housed the landing gear, but the gear deployed using hydraulic pistons in the inner wing. The wooden panel itself contained backup mechanical systems, simple cables and pulleys that could extend the gear manually if hydraulics failed. Chadwick had insisted on including these fail-safes when designing the wooden replacement. Most engineers considered them unnecessary. Chadwick had spent enough time around combat damage to know backup systems saved lives. Nicholson cranked the manual gear extension handle. On a standard Hurricane, this wouldn't work without hydraulic pressure to unlock the doors, but the wooden wing's simplified construction used spring-loaded doors that opened mechanically. The starboard gear locked down. The port gear stayed retracted, its hydraulics too damaged. A one-wheel landing was nearly as bad as a belly landing. The Hurricane would cartwheel, probably killing the pilot. But Nicholson had another idea drawn from Chadwick's teachings. Wood flexed more than metal. If he could land on the extended starboard gear, let the wing absorb initial impact, then gradually settle onto the retracted port gear, he might survive. He approached RAF Hawking with the precision of a test pilot. Airspeed exactly 85 millipalings, nose high, rate of descent minimal. The starboard wheel touched first, exactly as planned. The wooden wing flexed upward, absorbing the impact force. The Hurricane settled onto the starboard gear alone, wing bending noticeably under the load. Then Nicholson did something that would have destroyed a metal wing. He deliberately applied left aileron, forcing the port wing down. The metal wing dropped, its retracted gear grinding across concrete. Sparks flew, but the weight transfer unloaded the starboard wooden wing, preventing it from flexing beyond failure point. The Hurricane slid to a stop. Nicholson shut down the engine, climbed out, and examined the damage. The port wing was ruined, ground down to structural members. The starboard wooden wing showed stress marks, some cracking in the fabric skin, but remained fundamentally sound. Chadwick's laminated ash spar had flexed nearly 6 inches under the landing load without fracturing. The station engineering officer examined the wooden wing and delivered a verdict that summarized months of experience. That wing's taken more abuse than most complete aircraft endure. I want to know what the schoolteacher put in it. What Chadwick had put in it was understanding that flexibility wasn't weakness. Metal construction emphasized rigidity, structures that maintained exact shapes under load. Wood construction accepted deflection, using the material's natural resilience to absorb forces that would crack metal. The wooden wing had survived precisely because it could bend in ways aluminium couldn't. German intelligence finally discovered British wooden repairs in late 1941, and the revelation caused considerable confusion in Luftwaffe technical intelligence branches. A captured Hurricane forced down near Calais showed obvious wooden construction in one wing panel. German engineers examining the wreckage initially assumed it was a training aircraft, something cobbled together for flight schools using whatever materials came to hand. Then photo reconnaissance showed Hurricanes with mismatched wing panels operating from frontline squadrons. Luftwaffe intelligence officers requested clarification from their engineering staff. Were the British actually repairing combat aircraft with wood? The engineers confirmed it reluctantly. Yes, analysis indicated wooden structures in operational fighters, not complete airframes, but significant structural sections. This intelligence reached Reichsmarschall Hermann Göring's staff in December 1941. The reaction mixed disbelief and contempt. Göring reportedly joked that Britain was regressing to World War I technology, building fighters from furniture materials because they couldn't produce proper metal aircraft. The Luftwaffe High Command interpreted wooden repairs as evidence of British desperation, proof that RAF logistics were collapsing under sustained pressure. They were wrong. British wooden repairs reflected pragmatism, not desperation. Engineers had discovered that wood, properly used, solved problems metal couldn't. Battle damage that would ground aircraft permanently could be repaired in field workshops using locally available materials, and those repairs performed equivalently to original construction at a fraction of the resource cost. The German response followed predictable patterns. If Britain was using wood successfully, Germany should investigate similar techniques. Orders went out to Focke-Wulf and Messerschmitt to develop wooden repair procedures for combat damage. Both companies submitted proposals in early 1942. Neither succeeded. The German aviation industry had spent 2 decades perfecting metal construction. Their craftsmen understood welding, heat treatment, precision machining. Very few understood laminated wood construction at the level British furniture makers practiced instinctively. The adhesives German chemists produced failed under stress. The timber they selected lacked appropriate grain characteristics. The designs they created were too rigid, trying to replicate metal structures in wood rather than designing around wood-specific properties. By mid-1942, German attempts to copy British wooden repairs had largely failed. A few aircraft received wooden patches, mostly ineffective. The Luftwaffe continued relying on metal construction exclusively, accepting that battle-damaged aircraft were total losses when Britain would have repaired them. The contrast revealed something fundamental about technological innovation during crisis. Britain succeeded with wooden repairs because they weren't trying to prove wood was superior. They were trying to keep aircraft flying with whatever materials worked. That pragmatism, that willingness to use inferior materials if they solved the immediate problem, gave Britain a decisive advantage in logistics that the supposedly superior German engineering establishment couldn't match. Roy Chadwick returned to teaching in 1943, his wartime service complete. The Air Ministry awarded him an MBE for services to aircraft repair, a bureaucratic citation that barely hinted at his contribution. He'd kept hundreds of fighters operational through techniques that violated every principle of modern aeronautical engineering. He'd proven that sometimes the old ways worked better than the new ones, and he'd done it by ignoring what everyone knew and trusting what physics demonstrated. The wooden repairs continued until 1945, becoming so routine that nobody remarked on them. Post-war analysis estimated that wooden structures kept approximately 800 Hurricanes and Spitfires flying that would otherwise have been scrapped. That's roughly equivalent to 30 squadrons worth of aircraft, maintained without consuming the aluminium that fighter production desperately needed. James Nicholson received the Victoria Cross for his actions on June 4, 1940, the only fighter command pilot to receive Britain's highest decoration during the entire war. The citation mentioned his courage continuing the fight while his Hurricane burned. It didn't mention the wooden wing that had brought him home safely, or the multiple combat missions he'd flown in an aircraft held together by furniture-making techniques. Modern aviation students learn about aluminium construction, composite materials, advanced alloys. Few hear about the wooden repairs that kept the RAF flying during Britain's most desperate hour. The techniques weren't revolutionary, they weren't innovative, they were simply practical, using available materials to solve immediate problems without waiting for perfect solutions. Perhaps that's the deepest lesson from Roy Chadwick's wooden wing. Innovation during crisis doesn't require revolutionary technology. It requires understanding materials thoroughly enough to use them creatively. It requires ignoring conventional wisdom when physics suggests better approaches. And it requires the courage to trust that sometimes the school teacher from Guildford understands aerodynamics better than the experts who initially dismissed him as hopelessly outdated. The wooden wing proved that the most effective solutions aren't always the most sophisticated ones. Sometimes you win by using what you have brilliantly, rather than waiting for what you need desperately. The Luftwaffe had superior metals, better adhesives, more advanced manufacturing. Britain had furniture factories and a school teacher who understood that wood, properly used, could outperform metal in ways German engineers never imagined. That wasn't backwardness, that was genius.